Okay, so we're starting chapter 5 here. This is on continuous variables. If you go back to chapter 4, everything here was about discrete variables. So just as a quick reminder, a random variable is just a possible outcome of a random trial, but it's a quantity. Okay, X has to be a quantitative variable. And what makes it discrete is one variable whose values can be listed, and so that you can just count them. Okay, 1, 2, 3, 4, 5. If you can count them, it's discrete. All right. If you can't count it, if you can only measure it, then that's called continuous. So that's what we're studying here. Let's make a quick reminder. So for continuous variables, oops. That are quantities. That can't be counted, only measured. Okay, so you think about heights, which is the example here, or weights, or temperatures, or speeds. You can't count the speed as you're driving down the road. You have to measure it. Stuff like that. Okay, and generally speaking, of those types of measurements get really close together. You can be 6 feet tall, but you can also be 6.1 feet tall, and you could be 6.01 feet tall. And so because they come so close together, they form a continuous number line. And that's why we call it a continuous variable. Okay, so the histogram below gives relative frequencies for a huge random sample. What I did was I simulated 10,000 men's heights. Okay, I assumed the distribution was normal, which is bell-shaped, and I gave it a mean of 69 inches. It's a population whose mean is assumed to be 69 inches. Each bar has a width of 2, and the height is scaled so that the area of the bar is equal to the probability that it represents. So this represents the probabilities of all the outcomes. And the total area is 1, as you would always get. So men's heights are what type of variable? Is it discrete or continuous? Anybody?
Continuous.
That's continuous, correct. Okay. What's the class width for these bars? Anybody?
Is it 2?
Yeah, because it goes from 68 to 70 and so on. So good, the class widths are 2. Then the next thing says, okay, we can make the class widths smaller. So I think you can see from 68 to 70, you can see 4 bars there. So 1, 2, 3, 4. So I've sort of allowed the numbers to get a little closer together. With 4 bars in that range, what's the class width now? Anybody?
Is it half?
Yeah, 0.5 for the class width now. Now, again, what I did was to make these graphs is I generated a random collection of 10,000 men's heights with certain assumptions. Again, that the mean was, I think I set the mean to 69. The standard deviation was 3. And I told it to create a normal distribution of values. So they're not real men, but with 10,000 values, you can make the bars really skinny and you'll still get a lot of values falling into each. And the area of each bar represents the probability of a height being in that range. They're just relative frequencies. Okay, and then the histogram, I sliced even more. I don't know how many bars I have here. 1, 2, 3, 4. So there's 8 bars, there's 4 bars per inch, basically. So these are 0.25. So it says there's 100 bars. I still have, again, 10,000 men's heights. And so I still get men falling into each bar, and it makes a distribution that's almost a smooth curve. But behind the distribution, I actually did put in a little black curve there that represents what's called a normal distribution, which is the classic bell curve. Okay, so it's represented nicely by a smooth curve. So the symmetric bell-shaped distribution is called a normal distribution. Okay, now this black curve here is a probability curve. And the probability curve is called a probability density function. Isn't that beautiful? A lot of the formulas with continuous distributions are the same formulas for calculus for like a mean. And there's also a standard deviation. I said calculus, but I meant physics. The mean in physics is called the center of mass. But you have to know how the mass in some object is distributed. So in physics, instead of a probability density function, we have a mass density function to describe the density of mass at any location. So that's mass density function. The mean is the center of mass. And the variance is a thing in physics as well. It's called the moment of inertia. So all of the ideas in statistics for the mean, the standard deviation, they're all, and even the probability density, these are all stolen from physics. You take the word mass or mass distribution and you change it to probability distribution or mass density. Okay. Normal distribution, which is graphed above, has the following formula. We're not going to use this formula, but I like to put it in. It uses the z-score. So you do the exponent for e is -1/2. And then you put in the z-score here, which is x minus mu over sigma. I haven't done z-scores in a bit. Like that. And that gets squared. Okay. And then the whole thing is over sigma again and times the square root of 2 pi. So that is one nasty formula. And if you graph that, it looks like a perfect bell curve. You need to tell it what the mean is and what the standard deviation is. And that will define the bell curve. So different means give different bell curves, different standard deviations. That will change the width. The distribution was discovered by Abraham de Moivre. Abraham, I guess. And de Moivre is French, so it's D-E apostrophe M-O-I-V-R-E. Why is it important? Well, I'd say it's very common. That's why it's called normal. But I'd also say that sample means and proportions have normal distributions? Running out of space. So they have normal distributions under certain conditions is what I wanted to squeeze here. And the condition is you just have to pump up the sample size big enough. We'll talk more about that. Okay. I said that distribution is discovered by de Moivre. It was actually Carl Gauss, Carl Friedrich Gauss, who took the credit for it for a very long time. Gauss is a very famous mathematician and physicist. If you want to know the history of science and math, it's mostly a history of people taking credit for other people's work. And it's usually someone of power or wealth that gets the credit for something that a poor person did. So Abraham de Moivre was sort of a commoner. He wasn't wealthy or powerful, and Gauss was very wealthy and powerful. So naturally, he said he invented it. And of course, it was 50 to 100 years later. And naturally, people tended to believe him until much later. Okay, so let's keep going. It says, in the following lessons, we'll learn to find areas under a normal probability density function. Remember, the curve is called the density function. Okay, so we're going to be able to find these areas. The areas are the probabilities. Now, the simplest type of probability distribution plotted below is called a uniform distribution. We start with these because they're so dang easy. And then we'll learn to use Desmos to find areas under bell curve. So basically, areas are probabilities. And so we're going to have to find areas under bell curves. But it's easier to start with rectangles. And of course, I don't think you have to worry about, work doing any test questions on this one. It's just a nice intro. So let's go ahead and jump in. It says, what's the total area under this probability distribution? It's 1. The total area is 1, as always. Because the total probability has to be 1. What's the range of the variable x? Well, range is max minus min, if you want to remember that. So the way I've got it here is the max is b in the picture, and the min is a. So that's the range. So the probability density function is the curve that defines the height. So I just need to find out how high this is. We'll call that y equals whatever the height is. Okay, just remember the total area is 1. The height and the base multiply to make 1. That makes them reciprocals. 2 numbers that multiply to make 1 are reciprocals. So the base is b minus a. The reciprocal of that is 1 minus b over b minus a, sorry. Okay, so that if you multiply b minus a times 1 over b minus a, you get 1. So that's the density function on top. Y equals 1 over b minus a, like that. And I'll go ahead and write it down as the answer to that question. And then it says, what's the shaded area? This is P, the probability that X is between C and D. So C less than or equal to X less than or equal to D is how we will write that, but I'll put it into words. This is the probability that X, which is a random value, remember it's called a random variable because it's a result of a random observation. So that X lies between C and D. Okay, any questions? So you're gonna have to deal with that new notation for continuous variables. All right, any questions? I think I have an example here. Yeah, I worked really hard to come up with examples of uniform distribution, but this is my best attempt. So it says a children's day camp enrolls children from 5 years of age up to their 10th birthday. So they range from 5 to 10 years old, but on their 10th birthday, they're booted out. They can't go. If a child is randomly selected, age is a continuous random variable that ranges from 5 to 10 with probabilities distributed uniformly. So again, the total area is 1. Okay. The base, if we do the range, we need this distribution width. So the range is 10 minus 5. And that's 5. Okay, the height has to be the reciprocal of the base because this is a rectangle. Base times height has to be 1. So y equals what height? Well, that again is the reciprocal of the base, 1/5, which is, and if you divide 1 by 5, you get 0.2. Or you could say 0.20 if that makes you feel better. So that is the curve on top. It's y equals 0.2. And that's called the probability density function. And that's why I have that marked here on the y-axis. Any questions there? Now it looks like what I did here was asked you to compute a probability. So this one says, what's the probability the random child is between 6.5 and 9.5 years old? It says shade the region and then give the probability. Fine. So 6.5 starts here. 9.5 goes all the way up to here. So in pink, I'm sort of trying to shade this like that. Actually, I think what I'm going to do, I'm going to cheat a little. I'm going to draw a rectangle this way and set it on here. And maybe change the fill to that color. Okay, so there's my rectangle. Any questions? I need the base and the height. I know the height is 1/5, which is 0.2. Now I need that's the height of my pink rectangle. I need the width of that rectangle to compute its area. Okay, so that would be the highest value minus the lowest value. So if you do 9.5 minus 6.5, what's that?
3?
Yeah, so 9.5 minus 6.5 is 3. And so the probability, watch how I write this here, probability that X is between 6.5. So you say 6.5 is the lowest number. 9.5 is the highest number. And X is a random value between these. That's how you write it. Okay, and probability is area, which is base times height. Okay, the base is 3. The height is 0.2. So that's 0.6, which you can call, 0.60 if you like, which is 60%, no rounding there. So it's okay to write that with 2 significant figures or 1. Okay, any questions? So that's the very first type of continuous probability distribution that we do. Okay, simplest kind. You're not going to do anything that's simple, unfortunately, on an exam. Okay, but it's conceptually important, so that's why we do it. Any questions? So I go from the simplest distribution to something that looks just absolutely wildly complicated down here.
I have a question.
Yeah, go.
So I didn't know that on our first exam that you were going to allow us to use our notes. Is that going to be the same case for our second and third as well as our final?
I apologize for what I'm about to say,
Oh,
but
no.
your questions they need you. When you ask a question that's completely unrelated to the discussion, you should do that either during the break.
Okay, got
Like,
it.
you know what I'm saying?
Yeah, I do.
Okay, so let's keep stuff like that till a better time. All right. So we've got the area here as the probability, and now I'm switching down to something that's just complicated. Okay, this is a mountain lake stocked with 2 types of fish. The good problem like this, when you mix 2 populations together, you get the weirdest distribution shapes because each population sort of has its own curve. And if you mix 2 of them together, it looks like 2 curves where you have, 2 high points. Basically, you have a mode here, which is going to be close to the average for the smaller type of fish, which I don't know if I mentioned what type of fish they are. In other handouts, they're called bream, which is a teeny little fish, and bass has its own mode near the average weight for the bass. Okay, so with 2 modes or 2 peaks, you end up with a bizarre distribution shape. It still is a probability distribution, so the total area is still 1. The mean is 1.7 pounds. It says, and that's all based on a bunch of nasty math that I did to make this graph. Random variable is continuous, so we can compute the probability for any range of values, it says. So if we slide down here, look what I did. I sliced the curve up. And basically, you can use calculus to find areas under curves like this for any range of values for the weight of the fish. So that's all I did here is just did some numerical integration with calculus to find these areas. You can add them up. They add up to 1. They're very rounded, but they still add up to 1. Okay, it says note the distribution starts at 0. That makes sense because fish cannot weigh negative amounts. Okay, the curve does go on and on the right side. That's actually kind of important because we don't want to make a commitment about the heaviest fish in the lake because nobody knows, right? So it's good to let the curve go. We know that there's no fish less than 0 pounds. So it's good to have the curve stop on this side. But the curve should be allowed to kind of go out, but the probabilities just go to 0. So it says the distribution starts at 0, though the probability curve goes on and on. It's indistinguishable for 0 for fish weights above 5 or 6 pounds. It's never exactly zero, but it's effectively zero once you get to the heavy weights for the fish. Okay. And I don't remember what, if I researched what the average weight of a bass was before I did this. We're just going to pretend it's real. Okay. So when it asks for the total area under the curve, what do you say? You don't even have to add it up. What does it add up to? Total area equals what? What do probabilities always add up to in a distribution?
1.
Yeah, they always add up to 1. Thank you. Now, again, this it's a really complicated curve. So I did the math, most of the math for you in this graphic. And again, just to kind of see how, we need some way of determining these areas. It's either with calculus or sometimes there's a tool for looking them up. This one, I've just given it to you, so with a picture. So here they're asking for the probability of getting from 1.5 to 3.5, to 3 for the fish weight. So 1.5 starts here, and then it goes up to 3 there, and then you're just trying to find the area of that sort of pink thing that I colored. So you just add those up. So the probability is equal to 0.26, the first bar. It's not really a bar, it's first slice, plus 0.18 plus 0.09. And that's 0. What?
.52.
0.52. Okay, so this one includes the endpoints. Okay, this one excludes the endpoints, but is otherwise the same question. Oops. So it doesn't include 1.5 or 3.0. Now this is weird because what I'm basically asking you to do is to sort of compute the area again, but don't include those little thin black lines. So I'm going to go ahead and represent those black lines in white now. Okay, so I'm erasing the black lines in the graph. You see this? See what I've done? I didn't do as well there. There we go. So I've erased the black lines. Did the region get smaller? Remember, a line has no thickness. Did the region get smaller when I erase those, or is it the same region? Those lines have no thickness.
It's the same region.
It's the same, right? If you put a fence around your yard, it doesn't get bigger. It's still going to have the same area. If you take the fence out, I should say when you put the fence up, it doesn't get bigger. If you take the fence down, it doesn't get smaller. The fence actually doesn't increase the area because it's just too thin. Okay, especially an infinitely thin fence. Okay, so how is it different? I guess we would say this gives the same result. Let me change something real quick here. Okay, this gives the same result. Now, again, if you need a reason, I would say the vertical lines do not add area to the graph. So including the vertical lines doesn't change the area. Okay. So you just have to remember that when we say X is between 1.5 and 3, that X could be as close as you like to 1.5. It goes right down to 1.5. So it still kind of includes the same region. So that's nice to know. If there's an or equal, this one appears as, oops, my bad, hang on. This one says or equal, this one says or equal. This one just says less than, less than. Those don't change the probability computation. So you just ignore it. So the next question says, does it matter if we include endpoints when working with probabilities for continuous variables? No. Hey, look at this one. What's the probability that a fish weighs exactly 2 pounds? And I mean 2.00000 pounds. How wide is that as a region? Remember, an exact value is not an area, it's a line. Okay, when you say X is exactly 2, you're not giving a range, you're giving a single value. How wide on a number line is a single number?
It's not wide.
It's not wide?
I mean,
Yeah, the
It's-
width is, you're right, the width is 0, right?
yeah.
Do you agree? Yeah, so if the width is 0, then the area is 0, so the probability is 0. Okay, so the answer is 0. Lines with no width have no area. You're not going to find a fish that weighs exactly 2 pounds is the point. Close to 2, yeah. And maybe your scale says 2.0, but your scale's rounding to the nearest 10th, right? That's how scales work. They round. Okay, but if you got, an infinite number of zeros on your scale, it's not going to have, sorry, if you get an infinite number of digits is what I meant to say on your scale, it's not going to be an infinite string of random zeros. That's not random. Eventually you won't have zeros. It's just, this is a random fish. It's not going to be all zeros. Okay, so lines with no width have no area. So the probability is 0. Okay, any questions? Area is probability. Okay, so the next thing is we've got to go to section 5.2, which goes into the normal distribution. So this 5.1 is conceptually important, but I don't see myself asking much on an exam for 5.1. Okay, this would be a good time to ask questions about exams because I just mentioned an exam. So I can't remember who had asked something. Was that Danny? Did you want to ask your question about the exam?
Yes, my question was, will we be able to use our notes for the last 2 exams as well as the final?
The rule that I have to follow is that we always provide notes and any reference materials for looking up. Did I say notes? We always provide formulas like I did on the last exam, remember? Plus, we give you any reference materials for looking things up. Now, in COVID days, that means I'm going to have tools for you to compute different probabilities and stuff, and one of them is going to be Desmos. Okay, and I will give instructions on the exam for using Desmos, but it's not going to be an open note test. Okay. So you have every formula you need will be available, but you just need to know how to use it. And that you got to know in advance. All right, let's go to the next page. So now we're doing section 5.2. You can see all these bell curves. And so we're going to just study bell curves in this section. We're going to start with something called the standard normal distribution. That's a distribution of z-scores. So what we really do to all the different normal distributions out there is we standardize them by taking z-scores, and that has a very clever effect of making them all the same. Okay, so let's talk about this. In this lesson, we begin our study of normal distributions. There are many normal distributions, all distinguished by their means and standard deviations. All of the probability distributions are normal with different means and standard deviations, but they all come from the same formula. They all have a total area underneath equal to 1. Okay, so this is all stuff we sort of know. I've given you the formula for the normal distribution in the previous section. I don't think we'll need it. So it says important facts about normal distributions. First one, the mean and the median are the same, which means half the values are below the mean and half of them are above the mean. So the mean is just in the middle. The normal curve is bell-shaped and symmetric with respect to the mean. Again, that means the mean is the center of symmetry. The area under a normal curve is 1. Normal curves extend endlessly in both directions, but they zero out for values that are more than around 4 standard deviations above or below the mean. So the curve essentially zeroes out at 4 standard deviations up or down from the mean. Okay, that's always going to happen. The normal curve changes its curvature from upward to downward at 1 standard deviation below and above the mean. So that's kind of interesting. These points are called inflections. So here's the mean right here in the middle. Okay, this is 1 standard deviation up and 1 standard deviation down. Okay. And let me do it this way. I'm going to put a plus sigma there. So right here, let's do it this way. From here to here, I'm adding a standard deviation. Okay. And then going the other way, I'm subtracting a standard deviation. Okay. And where does that occur? Well, 1 standard deviation from the mean. And what happens on the curve at 1 standard deviation above and below the mean? You get this thing called an inflection. What the heck's an inflection? It's a wobble. When people say there's like an inflection in your voice, you're going, where you go from down to up or something like that. Geometrically, an inflection was where the curvature changes from a downward, like this, an upside down bowl. When it changes, you have an inflection point, and then it goes upward like a right side up bowl. 2 inflections, and the downward curvature is between them. Okay, now why is that important? Well, it's only important because it allows us to sort of look at a curve, and you can kind of guess what the standard deviation is if you figure out where the inflection point is. Standard deviation is the difference, is the distance from the inflection to the mean. Okay, so you could kind of like do this and then say this distance right here is the standard deviation. So you can kind of guess it. It's pretty accurate. Okay. So like that. So the question now is, well, what's a z-score and what's the formula? Okay, wait a minute. Z-score equals number of standard deviations from X to the mean. Okay, so the formula is you take Z, to compute it, you have to take X, you subtract the mean to find how far that is. And then you need to know how many standard deviations that is. So you see how many times the standard deviation goes into it. Okay. Now it says write the z-score below each tick mark on the number line above. So what's the z-score of the mean? How many standard deviations is it from the mean? Okay, Would you guys just unmute yourself? And if you can, maybe you can't, but how many standard deviations is the mean from the mean?
0?
Yeah, it's always going to be 0 here. Okay. Now, in the center, it'll always be 0 in terms of z-scores. What's the z-score when you go up 1 standard deviation from the mean? Another way of asking is, how many standard deviations is this value right here from the mean that I just circled? How many standard deviations from the mean?
+1.
Yeah, so z-score is 1 there. Okay, and z is 2 when you go up 2 standard deviations. Then z is 3 when you go up 3. Okay, if you subtract standard deviations, the z-scores become negative. So z is -1, -2, and -3 on the left. And what you just did by doing this, oops, is you standardized the distribution. Instead of using values from your population, like if it's women's heights or men's weights, instead of using values from the population, we will count how many standard deviations each height is from the mean. That's a z-score. And then from the z-scores, all the distributions are centered the same way. They are always centered at 0, like you see. The inflection point is always where z is 1 or where z is -1. Therefore, the standard deviation is the distance to the inflection point. It's right here. You can see from the picture what the standard deviation is. You can also see what the mean is. So let's see, what's the mean in z-scores? Don't look at the other values, just look at the z-scores. What's the mean? So the mean, yeah, the mean is 0 for z-scores, always. It's the same distribution shape. So we can say z-scores will still have this bell-shaped distribution. Now, the standard deviation is the distance from the mean to the inflection. How far is that?
1.
Yeah, so the standard deviation, oops, for z-score, any collection of z-scores is always 1. So you see how we're making all of the distributions out there the same? Just by taking z-scores, you end up with a new collection of numbers that always has a mean of 0 and always has a standard deviation of 1. So that's why it's called standardizing the normal distribution. And see, the title of the section is the standard normal distribution. You're making them all the same. You're standardizing them. Okay. So for any population of z-scores, the mean is 0. Okay, and the standard deviation is 1. Okay, the empirical rule applies to normal populations. You've seen this before, that 68% of values lie within 1 standard deviation from the mean. So that means that z is 0 in the center. And if you go 1 standard deviation out from the mean, you're going from z equals -1 to +1. And the probability of being in that range is 68%. Now, if you go out 2 standard deviations, that's going from z equals -2 to z equals +2. And the probability of being in that range is 95%. Okay, any questions? It's just the empirical rule, but I'm applying it to z-scores now. Okay, and then going 3 standard deviations, z goes from -3 to 3. The probability of being in that range is 99.7%. Remember, we said the distribution basically zeroes out at 4 standard deviations from the mean. So at 3 standard deviations, it's almost zeroed out. At 4 standard deviations, you can say it's almost completely zeroed out, although it never really zeroes out. But for all intents and purposes, it zeroes out. Okay, any questions about all this?
I have a question. So, how do we get 1 for the standard deviation of zero?
Oh yeah, it's just the distance to the inflection point. So if you look at the inflection point, just this part, just this part here. I did not mean to do that. Okay, this part, you can see the standard deviation is the distance from the center to the inflection point. And in terms of z-scores, how far is it from 0 to 1? The distance is 1.
Yeah,
And do you see that's why it's the standard deviation of 1? Does that make sense?
like from even if we try it from the standard deviation formula, we'll get the same thing, right?
Yeah, if you take a bunch of numbers and convert them to their z-scores, you have to compute the mean and the standard deviation. But if you convert a bunch of numbers to their z-scores, the mean will be 0 and the standard deviation will be 1.
Oh, okay. Yeah, that makes sense. Thank you.
It always happens. And there's a mathematical proof in the book if you care. Okay. Okay, so going on down here, we just want to do a little slicing. How are we doing time-wise? Yeah, we'll get through this anyway. We're going to still be a section behind, I think. Anyway, so it says adult men's heights are normally distributed with a mean of 69 and a standard deviation of 3. The graphic below depicts the distribution. We're going to label the tick marks with their z-scores below. Okay, again, the mean is 69, so we know we can put a 69 right in the middle. Okay, and the tick marks here are 1 standard deviation apart. The standard deviation is 3. So we're just going to add 3 to the 69 to get 72, and then just keep adding 3. There's 3 standard deviations above the mean, and then subtracting 3 on the other side. Okay, that's 3 standard deviations below the mean. It also says to label the z-scores here. So the z-scores in the center, z is 0 at 69. Okay, that's called standardizing when you switch to z-scores. Okay, and so on, z equals 1, z equals 2, etc. Okay, any questions so far? Now, I want to label these areas, and we're supposed to do it using the empirical rule. So very quickly, this region that I'm outlining in red, that's the 1 standard deviation region. What's the total area of what I just outlined in red?
Is that 68%?
Right, which is 0.68, but you see I have it sliced in half. So what are the 2 halves?
34.
Good. So each side will be 0.34. Okay, so this is just based on the empirical rule, which is the graphic on the top here. Now, harder, look at this region in red. What's the area?
95.
0.95. Now subtract out the 68 part. I want to get rid of this part. So subtract out what that is, 0.68.
27.
And divide by 2 to get this one and this one. Does that make sense?
Yeah, 13.5.
Okay, 0.135 for both of those. See, we're kind of breaking down this probability distribution based on what we know about the empirical rule. Unfortunately, we got to keep going. It's almost done, but a little bit more of this part. What's that total area?
99.7.
0.997, subtract out the middle, which is what? I'm getting a little messy here. Subtract out the middle. What's that?
4.7.
So you did 0.997 minus 0.95.
I get 0.002.
0.997 minus 0.95.
I'm just kidding. 0.047.
I'm thinking, and you got to divide that by 2 because you've got this part here on the left and right. So what do those make?
0.0235.
That's exactly right. 0.0235. You're never going to do this on a test either, so don't panic, y'all. It's just kind of taking what we know and sort of developing our brains on how this works. All right, one more time. The total area, oops, hang on. The total area of this whole monstrosity is 1. Okay, now we want to get these 2 skinny little tails here and here. Got it? So you have to take 1, which is the whole distribution.
Would it
And
be 100 minus 99.7?
Yeah, 0.997 and divide by 2 again. And this one's gonna be super small.
0.0015.
Again, that's perfect. Thank you. 0.0015 on both sides. Okay, so now if we wanted to, we could do all kinds of probabilities here. I hate to do this to you guys, but they want us to copy those in. So you're going to hate me for just copying and pasting these down to the next graphic. So this is, again, the process of standardizing a distribution. I think the idea is that when you switch to z-scores, the only thing that changes are the letters on the number line, but the areas and the shape of the distribution are unaffected.
How did you get the last measurement, 0.0015, or computation?
Yeah, so we took the whole distribution. Let me just do it this way. We took the whole distribution and we subtracted out the 0.997. So the whole distribution is 1. If you subtract out the 0.997, you're getting these 2 skinny little tails right and left here. Okay. And then you have to divide that by 2.
Thank you.
Yep. Okay, but so the only difference here is they're asking us to put in z-scores on this distribution. So we labeled this with a z-score here. And again, z starts at 0 in the middle and goes 1, 2, 3 on the right, -1, -2, -3. And again, this is called the standard normal distribution because it's been standardized. All of them become the same distribution. By using z-scores. Okay, and it's really common. How are we doing? 11:10, so we got a half hour. All right, we'll get through it. It's really common to use a table to look up areas under a curve. We've just used the empirical rule to slice it up into increments of a standard deviation. Okay, 0, 1, 2, 3, and so on. But what if you have z-scores that aren't whole numbers? That'll actually be the case almost all the time. Your z-scores are not going to be whole numbers, and you're still going to need the probability. Okay, so the question is, what do I do to get probabilities for non-whole number values of z? And the answer is you need some tool. You can use tables like this monstrosity here. I don't know, there's something that makes me really happy when I look at this. Isn't that sick? I just love looking at these horrible messes of numbers. Feels good, especially during COVID. I don't know, it's just comforting. The good news is you don't have to use this if you don't want. You can use Desmos. So I'll show you how to do it in Desmos as well. So the density function for the standard normal, see if I show you the old density function, I'm gonna just write it up here. The density function was, no. The density function was y equals e, I'm gonna erase this to the -1/2, and there's an x minus mu over sigma, that's the z-score formula, and it's squared over sigma square root of 2 pi, okay? So that's the formula for the normal density function. And there's a couple ways you can look at this. You could say, well, this part right here is the z-score formula. So we're just going to replace that with a z. Okay, so it's going to be e to the -1/2 z squared. And then the standard deviation of z is 1. So the density function essentially turns into, if you just look at that, I have to write y equals still e to the -1/2 z squared over the standard deviation, which is 1, I'll leave that out, times the square root of 2 pi. So, and again, we don't use that. If you've taken calculus, I think you might be able to take that formula and say, oh, I know how to find areas under a bell curve, because that's what you learn in calculus. But we don't use that formula. We use this. Okay, any questions? And this is in the front of, I think it's inside the front cover of the book. So if you need a quick reference to it. Some of you may choose to use the table. It's hard because, you know, all of the curriculum is built up around tables. We don't, when statistics curriculum was sort of put together, there was no assumption you'd be able to use Desmos during exams. So the materials are created so that you will use, well, you know, that you're going to be using tables to look up probabilities. You know, so the book assumes that, everything assumes it, because that's how it's taught. But during COVID, I'm going to give you another option. That's all. I'm going to do it this way, but I'm also going to give you an option in Desmos. Okay, so let me just go ahead and slide down here. Where's the description? There it is. Okay, so it says to find probabilities for normally distributed variable X, we compute z-scores and look them up on table A1. The table gives areas to the left of any z-score, now rounded to the nearest 100th. Okay, so on the table here, you're looking up your z-score down this way to the nearest 10th. These are negative. Okay, and then the 100th place go this way. And I would say the same thing for the second side of the table, but they're positive for the z-scores. So I'm actually just gonna, sort of copy this all over. And maybe change the word negative to positive. That's a little too hard to read, actually. Okay, so that's how the table works. And we're just going to practice using it. And then I'll show you how to do it in Desmos. Okay, any questions? Okay, and you'll see that I'll provide this handout pretty routinely when we need it in the notes. So it's nice if you know where this is. Again, I don't know if I keep putting it in here. I think at this next section, I also put a copy there. So you can see me putting copies of this table wherever I think maybe you'll want it. But again, there's Desmos, and it's also inside the front cover of your book. It's also in the back in the appendix of the book as well. It's all over the place. Okay. So let's go ahead. It's again, this thing gives areas to the left. So I think I want to highlight that. So let's just make sure this is absolutely clear. This table, so this table gives areas to the left of any z-score. That's what you need to know. You're getting the area to the left. So it's going to be sort of like the way we chopped this thing up to get all the areas into the bell curve. We're thinking, oh boy, if I want to figure out the area to the right, I have to do 1 minus the area to the left because the total area is 1, stuff like that. So that's what makes the table sort of a pain in the butt, is it only gives areas to the left. Okay, so the first problem, this is what you want. If you want the probability that z is less than 1.29, I like to draw a picture first. Okay, so maybe we'll put a 1.29 on here, 1.29. These are z-scores. So remember, those are centered at 0. And then the area to the left is over here. And I would very much encourage you to draw these curves. The stronger you are as a math student, the less you'll need to keep drawing these curves. But I think that if you struggle in math, I think there's something just sort of important about you did sort of the mental development of trying to connect the area of the picture to the probability. Okay. The shading part also very important. Okay. Anyway, so you just look up 1.29. So if you look at this table, that's a positive z-score. Okay, so I'm going to zoom in here. I was going to try and zoom in. And for the nearest 10th, you're going from the z-score down to, what did I say, it was 1.29? Yeah, 1.29. So you go down to 1.2, and then the 0.09 is over here. So again, to the nearest 10th, it's 1.2. But for the 100th place, you have to add a 0.09 to 1.2, and those add up to 1.29. Here's the 1.2. Here, that's 0.09. Those add up to 1.29. So the 9 is the 100th place. Is that clear, everybody? I know that you're going to probably want to hear that again a few times eventually. Anybody have any questions? Now, you can see the probability here is 0.9015. And that's the answer to the question. It's just asking for the area to the left. That's what I drew. Less than means left. So what was it again? 0.9015. That's the answer. So just a lot of slicing up on a bell curve is what we're doing right now. Any questions? Now, the next one's really similar. Let me move that last picture I drew a little bit. Next one's really similar, but it's a negative z, and it's still asking less than, which means to the left. So let's go this way. So negative 2.53 is on the left here. I'll just go ahead and put it there. But this is going to be basically the same thing. Okay. Like that. Again, zero's in the middle, so that's why I know to put this on the left. Okay. And we use a negative part of the table. Okay, so I'm going to zip up to that real quick. So negative 2.53. So I think I'll just go to the negative 2.5 down here, and then 0, 1, 2, here's 3, and then up like this to make that connection. So 2.5 and the negative 0.03 make negative 2.53, and the probability is really small. 0.0057. So this would be a very unlikely event. Remember, z-score is the number of standard deviations from the mean. We have a rule for unusualness. Unusual values are 2 or more standard deviations from the mean. This thing's 2.53 standard deviations from the mean. This is an unusual value, and unusual values should be rare or low probability. The probability here is 0.0057, which is less than 1% chance. Okay, any questions about this? 0.0057.
Yeah, I have well, not specifically that one. I was just looking at because you have the greater than or equal to.
Yep.
Does that line make any difference? Like,
Do you remember the discussion about how thick a boundary is, like the
Right.
fence? Remember that?
Yes.
Boundaries don't have thickness on a continuous variable. They're razor thin. So they don't make the region bigger geometrically.
Okay.
So it will not change the answer. I put that in there just so we would have this discussion that you've just brought up.
Okay. Is there even then what's the rationale between even putting it there?
Maybe because I'm messing with your head. It's something along those lines of just you knowing more and understanding the subtleties makes you a stronger student.
Okay, got it.
Okay. So what did I say this was? This is 0.0057 looks like. Okay. Next one is a greater than. So that's going to look a little different this time. So I'm just drawing another bell curve here. But this one, the cutoff is 1.67. So remember, 0 is in the middle. 1.67 is going to be over here. It doesn't matter where, it just has to be on the right. And then we're going to shade that. And then we're going to tell ourselves greater than is the opposite of less than. Okay, so you just remember the just as a reminder, the probability of A is 1 minus the probability of A complement. A complement is an A with a bar over it. It means the opposite of A. Okay, so this table doesn't do greater than probabilities. It does less than probabilities, which is to the left. So when you see greater than, you have to think, ooh, that's 1 minus rule of complements. The probability that Z is less than, I'll put the or equal in just to mess with your head, 1.67. Okay, now what does that mean? Well, I think we better look up 1.67 in the table. Okay, so now I'm going back up and looking for 1.67. So I'm going to erase some of my prior mess. 1.67. So I have to go down to 1.6. 1.6 and then out to 07, which is right there. Like that. So it looks like the probability is 0.9525. Again, the 1.6 plus the 0.07 make the z-score, which is 1.67. They have to combine those two, the nearest tenth to the plus of the hundredths place. 0.9525. Okay, any questions? So 1 minus 0.9525. Anybody? Anybody? 04 something something.
0.0475.
That's great. Thank you. 0475. Okay. One more. So this is going to be the hardest one. Not computationally hard, super easy. The conceptual part's the trick. So this one goes from 2.15 to 3.11. Again, this is always z-scores. We're not doing anything but z-scores right now. We'll get away from z-scores in the next section, and the process in the next section will be to take your woman's height and convert it to a z-score. So it becomes one of these problems. Okay. Put in the two, again, zeros in the middle. The proportions are all wrong on the picture, but that's okay. 2.15 and 3.11, something like that. Shading between them. By the way, this covers the last possible case. We're basically trying to make sure you can hit them all. Anybody feel brave about doing this one? See, I can, maybe I should have done the picture this way. So this might be more instructive. I'm just changing my shading. So let's see, if I was to shade the area to the left of 3.11, it would look like this. And of course, when you look up 3.11, that's what you get. What I've just shaded in green. Now, if you look up the 2.15 area, I should switch colors, because what you'll get with 2.15 is what I'm shading in blue. So what should I do with these two areas? .11 gives you everything to the left. That's too much. So what should we do with the 2.15 area? Oh, they're not talking. Stressful. Okay, so what you're going to do is you're going to take the probability that z is less than 3.11, which is the shaded green part. And then you're going to subtract out the blue part, which is the probability that z is less than 2.15. Okay, again, the table only does less thans. So you have to frame everything in terms of less thans. Okay, so here, the 3.11, let's just jump up to that real quick. Now 3 point, that's gonna be way down there. So the 3.1 is here. Here's 0, 0, here's 0, 1. Okay, so maybe you can see, sort of see that. Okay, so what's the probability? Anybody see it?
Wait, why are you using that table instead of the other one?
Because these are positives and the other one's negatives. If your z-score is negative, you use this, the one on the left.
Oh, yes, I thought you were actually using the left, but I see you're using the right. Sorry.
Oh, I get you. That's a little confusing, right? Let me get rid of it. There. Okay, so, and you get 0.9991, right? So we can go down here and put down, the first one was 0.9991. minus, now do 2.15. So going back up. 2.15. So here's 2.1, and I have to go out 0, 1, 2, 3, 4, 5 to here. Like that. And I think you see the 9842 there. That's what you're subtracting. So these are all real close to 1. 0.9842 was the next one. Could somebody subtract those real quick and just shout it out?
0.0149.
Think, okay, 0.0149. Can we get a confirmation on that?
I got the same.
Perfect, thank you. All right, so how are we doing? 11:33. All right, let's summarize the three different scenarios. We have the less than problem. Both of the first two. Okay, then next we did greater than. Okay, then we did in between. Okay, those are the three scenarios. So for probability that Z is less than A, you just look up Z, sorry, look up A. I'll just say Z equals A, the endpoint on table A1. And give the associated area. Okay. For probability that Z is greater than A, that's when we use the rule of complements. We look up Z equals A on table A1. And give 1 minus the area. Okay. Now, for the probability that Z is between A and B, that's the in-between problem. We looked up two areas and we subtract the big one minus the small one. So you look up Z equals A and Z equals B to get two areas. And then you give the large area minus the small area. You'd never do it. The probabilities have to be positive, so you can't end up with a negative. You got to do big minus little here. That looks like a Z, so we're going to make that look again like a 2. Okay, that's it. I want to do a real quick reverse problem here. So just to show you, they want you to find the Z-score that goes with the right tail of area at 0.025. So just real quick, I'm going to draw this and put an area of 0.025 down. Right there, 0.025. Okay. We need the area to the left. Okay, so the table only works with areas to the left. So this would be 1 minus 0.025, which is 0.975, I think. I'll put a 9750 here. Okay, there's a big question mark here for the Z-score. That's what they're asking for. Okay, if you go to table A1 and you find something close to a 0.9750 in the body of the table, not on the edges, that would be able to tell you where your z-score is. Okay.
Why isn't the z-score in the middle of your drawing?
You mean you don't like this z-score here?
No, you know how normally we put the 0 in the middle?
Oh, okay, so the 0 would go here.
Oh, okay, I thought the question mark was oh, the question mark is,
That's the z-score I'm being asked to find.
okay, got it.
Okay, so I found the area to the left is 0.9750. So you're just sort of using the table backward. You're going to the middle and looking for a 0.9750. So this is approximately the area to the left. And so you have to find that on the table in the body of the thing. So it's sort of horrible. You have to scan all these numbers for 0.9750. You'll actually find it if you look right, not that one. Where are you? Here. So, caught it. And you go out to the edges, it'll tell you the z-score that goes with it. So in this case is 1.96. So that's just using the table backward, not a big deal, but a little bit of a headache. So on the edges, you see the 1.9 and the 0.06. So that tells you that Z is 1.96. Okay, I want to take it. I don't know if you can give me just one more sec. I have just a couple of minutes left. I need a blank spot here. So what I'm going to do is add some notes in Desmos. And I'll just show you how that works real quick, but let's just put it over here in the margin. So, and you can find a place. So in Desmos, you would enter normal dist. Let me get a magnifying glass here. Oh, good Lord, they went nuts. So hang on a second, y'all. I don't know what I did. Oh, heavens. Okay, let me try again. Okay, so normal dist, and you have to put a 0,1 in parentheses because the normal distribution has a mean of 0, the z-scores do have a mean of 0 and a standard deviation of 1. I'm going to move this over a skosh. And close the parentheses. Like that. You have to click the checkbox that says cumulative probabilities, which are the areas underneath. Okay. And then the min equals blank. The max equals blank. You can fill those in. You can leave the min blank if there isn't a min. You can leave the max blank if there isn't a max. Okay, so very quickly, I'm going to jump. I'll come back to these notes for those of you guys who are still scrambling. So just be patient while I show you how this works. So I'm going to pop. Hang on, I got to open a window. Okay. New share, this guy. So this is actually super easy, and I'm happy to let you use this on an exam. And I'll give you the instructions on the exam as well. So then the exam will say normal dist, and then you do 0,1. You have to tell it the mean is 0, the standard deviation is 1. Okay, I'm going to add something. You want to click on the cumulative probability here, so you click that. And then I'm going to add to the notes that you should click on this magnifying glass right here to kind of make a nice bell curve in the graph. and you just put in the min and the max. So let's do that last one that we did for Z between two numbers. No, actually, let's do Z less than 1.29. So with the less than 1.29, there's no min. So you just put 1.29 as the max. And you can see it's 0.9015, which is exactly what we got on the first problem, 0.9015. This is actually a little more precise because it's 90147. Okay, that's the first probability that we did. The next one was negative 2.53, so I can delete the max, put a negative 2.53 in, and it shades a little tail down here. It gives 0.0057, which is exactly what we got. If there's no max, you delete it, and it will go back to infinity for the max. If you want to put a min in, like the third one, you would put in a 1.67, and it gives 0.047 and a 6 is what it would round to. What we got was 0.475, which I think might be a rounding error on the table. Somebody's got a rounding error. So anyway, 0.475 or 76, no, it's 0.475. I read it wrong here. 0.475, so that's good. That's the third one. And the fourth one, and again, that's with no max, and it changed it to infinity. The last one has a min of 3.11. Nope, that's the max, my bad. 2.15. And the max is 3.11. And you get 0.0418, which once again, 041, which we got 0.0419, which is within the rounding error, no problem at all. Either one of these is a great answer. And we're done. All right, so, okay, so we're working on section 5.3. This is on the non-standard normal distribution. Just a reminder, the standard normal distribution is a distribution of z-scores. So it's a bell curve, but on the number line are number of standard deviations from the mean, which is a z-score. And that's all we learned how to work with last time. So obviously we need to go beyond the z-scores and do probabilities for any population that's normal. So it's pretty straightforward. If we work with a population that's normal, we would always convert values that, that we need to look up to z-scores first. And then once we have z-scores, then you have 3 different types of probabilities that you could compute. But it's no more complicated than that. I think it's worth reading this this review that we've got here, just so you can get all of the ideas in your head again. So again, a quick review of normal distributions. First fact is that the mean is the same as the median. So that just means that if you divide the distribution in 2, half of the distribution is less than the mean and half of the distribution is greater than the mean. Okay, and that's the definition of the median. Okay, so the mean and the median are the same. It's bell-shaped and symmetric with respect to the mean. The total area under the curve is 1. The curve sort of vanishes at about 4 standard deviations above or below the mean. It technically goes endlessly. But the probabilities kind of round off to 0 after about 4 standard deviations above the mean. We talked about inflections where the curvature changes from a downward curve to sort of upward curves, and the inflections occur exactly 1 standard deviation above the mean and 1 standard deviation below the mean. Okay, we only explain that fact so that you can kind of think about, oh, well, if I know what the mean is, the distance to the inflection is a standard deviation. Okay, and so you can kind of visually guess what the standard deviation is. All right, and so again, we're just finding areas under a normal curve right now. Let's just kind of review where we find normal probabilities. We can do either table A1, which we introduced last time, or Desmos command. Oops. The command is just normal dist. And then you give a mean of 0 and a standard deviation of 1 like that. And then you want to check off the cumulative. And then click on the zoom, which looks like a funny little magnifying glass like this. Okay, and if you just go through that process, you'll be able to do exactly what we did. So table A1 gives areas for what probability distribution? Technically the standard normal distribution. Now what makes it standardized is that it's a distribution of z-scores. Okay, so we need to, well, I guess I should, it's asking this question right here. The standard normal distribution of z-scores, the standard normal distribution is the distribution of z-scores. So it's a little redundant. Okay. And the non-standard normal distribution is any distribution that's normal. Just remind you, there's a lot of those, and so remember these are all different normal distributions. So they're all bell-shaped. They're all centered at their mean, and the total area under each one of them is 1. So there are many normal distributions, but there's only one standardized distribution of z-scores, which is where we just take values like here, and we can convert them to their z-scores. And that's called standardizing. And then all the populations become the same. And remember, a z-score is just the number of standard deviations a value is above average or below average. So let me go back to this picture again, right here. So when you're doing z-scores, on this one, 69 is the average. So its z-score is 0, and the mean of z-scores is 0. If you go one standard deviation above average, then the z-score will always be 1 there. And the standard deviation of z-scores is always 1. Okay. 2 standard deviations above average, z is always 2. And then if you go 2 standard deviations below average, z is always -2. So z counts how many standard deviations you are from average, and it's negative when you go below average. Okay. So that's just kind of a quick reminder of how that works. You got that? Yeah, we're good. So then this discussion is about converting from z back and forth to x. Okay, so if you have a value of x that needs to be converted to z, you've got this formula, and it goes on the z number line. If you solve this equation for x, well, I can go ahead and put this to convert value x to a z-score. Z, as we've seen before, is x minus mu over sigma. A little algebra, you can multiply both sides of that by sigma, and you get z sigma is x plus mu. Sorry, minus mu. Boy, oh boy. X minus mu. And then if you add the mean to both sides, you have z sigma plus mu is x. So that's a formula that will take it'll take z and convert it to x. So x is, well, you can write it as mu plus z sigma. That is the mean plus Z standard deviations. Why would you take the mean and add Z standard deviations? Because X, by definition of Z, is always Z standard deviations above the mean. So that's all that computation is doing. Okay.
Can you repeat
So-
that, please? What?
Okay, so I think what you want me to repeat is this, why this equation makes sense.
Yes, please.
Yeah, the Z-score is the number of standard deviations that a given value is above the mean. So that's, I'm assuming you understand that.
Yes.
Z-scores count that. So if you take the mean and you add Z standard deviations, that's how you learn the value of X. So like if it's someone's height and you know there are 2 standard deviations above the mean, you would take the mean height and add 2 standard deviations to figure out how tall they are.
Got it. Thank you.
That makes sense?
Yes, please.
Yeah. So I'm just saying this equation, if you think about it, it totally makes sense as long as you know what a Z-score is. Okay, now what we really need to be able to do is just to do probabilities, and these will be the last types of problems that are on your test next week. Just if I did 3 problems like this and maybe 1 with the percentiles would be good to go. So let's go ahead and try out a few of these. So this one says the probability that X is less than 71.3. Now, these are women's heights here. The mean is 66, the standard deviation is 4, and it says that the distribution of women's heights is normal. So we know we can use the normal curve to do a probability for a woman's height. So the first thing you need to do is a Z-score. So for the Z-score, it's always X minus mu over sigma. And X is the boundary value. So we're saying that X is less than this boundary value, 71.3. What you're converting actually is the boundary value because you, in the end, you need a boundary value for Z. Okay, now you put in the 71.3, mu is the mean. So that turns out to be 66 as given in the problem. And the standard deviation is 4. And again, that's given as well. Okay, so the mean is mu. Standard deviation is sigma. Okay, so it's a simple computation, 71.3 minus 66 over 4, like that. And I'm getting my calculator going and I'll wait for you guys to give an answer.
I got 1.325.
That was so fast. That's what I got too. So let's call it 1.33. Now I'm doing to 3 places because that table that we use only goes 2 places after the decimal. I'll draw a little sketch of that. But right now, just to let you know, what we usually do is we rewrite the probability in terms of Z. So just the letter X changes to the letter Z because you're converting to Z-scores. And you're saying that X is less than 71.3, but that means its Z-score would be less than 1.33. Okay, now does everybody understand the logic behind that? You're just saying it's the same event. You know, someone's height is less than 71.3 inches, but that's the same because that is 1.33 standard deviations above the mean. That just means that the Z-score randomly is less than 1.33. It's the same probability. Okay. And from there, you can use table A1. Let me go ahead and draw a sketch real quick here. So I'm just going to put in the 1.33. We're shading to the left on that. And again, I think especially if you struggle with these things, the shading and just drawing, it's a good practice. So I'm only drawing the z-score here, and the mean, remember, for z-scores is 0, so I'll put that in the center. She's above average. She's 1.33 standard deviations above the mean, so I make that to the right of 0. Okay, and then if we go to table A1, you would, for your z-score, you want to go down to 1.3. And then the hundredths place is the other 3, 1.33. So 0.03 plus 1.3 is 1.33. And you sort of just come in like that. Now I think there's another copy of the table at the bottom here. So I'll go down 1.3 here, and then 0, 1, 2, 3, I think is this one. Okay, so I'll just circle that. So hopefully you can see what I've done. Does anybody have questions about this? Obviously, you need to be able to do it this way or in Desmos, which I'll show in a minute.
Why did we go 3 to the right?
Because the z-score is 1.33. So the 1.3 here is that.
Right.
And then the second 3 is this other.
Oh.
So the top is the 100ths place.
Oh, okay.
Yeah.
Got it.
super important, because we're gonna use this table a lot. Okay, and again, the probability there is 0.9082. Does anybody have any questions about this?
Thank you.
No problem. I'm here to help. Okay, anybody else? Okay, I'm gonna wipe that up a little bit here. Okay, 0.9082 is the answer on that one, so let's go back. So all you have to do is say that this is equal to 0.9082, and we got that area to the left, 9082, and in the table, 0.9082, and that's just basically the process. Okay, so any questions about this again? The next one's just like this, but it's a greater than problem. And I remind you that on the greater, the table only does less than problems. Greater is opposite than less. So you have to use the rule of complements on that one. But let's just go one step at a time. First, the z-score. And the mean does not change until someone changes to a different population. The only thing that changes is the value of x, which is the boundary point, this 59.6. Okay, but the mean will still be 66. And the standard deviation will still be 4, like that. Okay, and then I'll wait till somebody shouts that out. I'm typing it in myself as I speak.
Negative 1.6.
Exactly right. So I'm going to write negative 1.60. So we have that hundredths place on the table. Okay, now this one is z greater than negative 1.6. Now you have to remind yourself the table doesn't do greater thans, it only does less thans. So you have to do the rule of complements here. Technically, what's happening is you're doing 1 minus the probability that z is less than negative 1.6. So this is what's actually happening. Okay, so let me go ahead and draw the picture. So I'll put in the negative 1.60 here. Just reminding, this is on the negative side of the table. So you go down to negative 1.6. And then just over to the first column, 0.00, because it's 1.60. Okay. All right, so, and again, just also as a reminder, the table does not give that directly, it gives it indirectly. So we're gonna look up negative 1.6 and get what we don't want. So let's look at it again here on the negative side of the table. Okay, so hopefully you're seeing what I see. Is there any question about this? So it's a 0.0548. But that's the probability for being z to the left, and we're supposed to do z to the right, 0.0548. So I'll put that here, 0.0548, which is this on the left, 0.0548. But we want the area to the right. I'm going to try and make a little space for this. Okay, so we have to do 1 minus that, 0.0548. Okay. Anybody do that?
0.9452.
Great, thank you. So that's actually the answer to the question once you do the rule of complements. Okay, again, are there any questions? Okay, one more. This is one of the in-between problems. So we have two z-scores to compute. So let's do them individually. We'll do the big one first. So with 56.2, z is x minus mu over sigma. As before, mu and sigma are the same, but x is the boundary. 56.2 minus 66 over sigma, which is 4. Okay, so let's all do that. Tell me a mistake. I keep getting a value I know is wrong. So anybody get something for this one?
Negative 2.45.
Yeah, that's what I got too. Thank you. And then we have to do the other boundary now. Okay, and we'll round to 2 places. Anybody?
Point 6.3.
Yeah, let's go 0.63. That sounds great. So that so the problem changes to the probability that z is between these two numbers. So negative 2.45 on the left, less than z, less than 0.63 on the right, like that. And just as a quick reminder, I know I talked about this, but I'm going to slide back up and just read this part again on the last thing. Where is it? Okay, so it was the probability that z is between a and b here. You look up z equals a and z equals b to get 2 areas and give the large area minus the small area. Is there any question about that? So you have to look up the 2 z-scores and just subtract the areas, not the z-scores. Please don't ever subtract the z-scores. There is no reason to do that in any case. Okay, so I think I'll do the z-score lookup down here. So I'll do the 0.63 first because that's going to come out bigger. So you go down to 0.6 and over to 0.03. I'll do that in a second. For the other one, your z-score is negative. So you're going to go down to z equals negative 2.4 and over to 0.05. Okay, so first the 0.63. So that one comes out as 0.7357. Is there any question about that one? Okay, 0.7357 is the first one. So I just put that in right here. Okay, and then next we're going to do the negative 2.45. Okay, so let me go down and grab that. Yuck. Okay, so 2.4 negative. Here we go. Negative 2.4. Okay, 0, 1, 2, 3, 4, 5 to there. And again, that's a negative, so you have to use the left side of the table. Any questions? So it's 0.0071 on that. So those are the areas under the bell curve. And all you have to do now is just subtract the areas to get a final answer. Okay, so so on this one, you're going to do the big area, 0.7357. Subtract the small area, 0.0071 for a final answer. Anybody?
$0.7286.
Thank you. 0.7286 is correct. All right, so now you're doing normal probabilities. I think I'll show you, I gave the instructions for Desmos up here somewhere. So I think I'll show you the Desmos approach as well. Here is the command and the process. It works pretty well. So I'm just gonna keep this open on my iPad, but then do them again.
I have a question.
Yeah.
So this entire time I thought that when we're looking up numbers on the table, I
Mhm.
thought we were looking for the z-score.
We are.
Oh, okay. So, but the rule says to subtract the area.
Yeah, but we're looking up the z-score. I mean, first you started by looking up a z-score,
Yes.
and then, well, yeah, the z-score, and then in some cases you have to subtract areas, but you're not subtracting z-scores. You're looking up z-scores to get areas, and then sometimes you have to subtract areas.
Okay, thank you.
Yeah, there's two cases. So there's two cases where you subtract and only one case where you don't. Okay. Now, again, to me, this is all really tedious. And I think it's worth just looking at Desmos real quick. So let me do a share to my browser. And I'm going to punch in Desmos real quick. And so the command I put in for you is normal dist, and you have to give the mean and the standard deviation. So the mean is 0, standard deviation is 1 for the normal distribution. Then I also mentioned you should check find cumulative probability. And I finally mentioned that you should click on the magnifying glass. Okay, so you get a nice bell curve there. Now, all you have to do is put in mins and maxes, and you can just keep reusing this. So on the first one, the max had a z-score of 1.33. So if you just type in 1.33, you have the probability 0.9082 right there, which is what we typed in for the first answer. Okay, is there any question about that? Now, if you delete the max, it goes back to infinity, just FYI. Because the second problem has a min of -1.60, but no max. -1.60, and you get 0.9452, which is the answer we got. So there's no rule of complements. You don't have to subtract. It just knows, you know, I'm saying the min is -1.6. So this goes to the right for infinity. We have to use rule of complements on that one. But obviously the software is smart enough to do that for us. Okay, any questions? So exactly the same answer. It's much quicker, much simpler.
Is it always 4 sig figs?
Well, I mean, let's just do that because it's easier on me if everybody's getting the same. So let's do 4 sig figs. I wouldn't fault you for doing 3 because technically the rule for probabilities is 3. Okay. But it's better for my sanity if we all do 4 on these, but it's not a big deal either way. The last one had z-score between -2.45, and that was the min, and the max was 0.63. And so here it says 0.7285. We gave 0.7286, which is pretty close. They're off by 1 in 10,000. So that's negligible. The computer is actually more accurate because there's less rounding involved on the computer. Okay, any questions? If you use the tables here, you're using 2 rounded values, and that just kind of propagates the error, the small error in those computations. But again, these are really close, and so both answers are good. Okay, 7285 here, 7286 from the tables. Okay, any questions? Okay. What do you think's better, Desmos or the tables? Any opinions? I'm always curious. What?
It all sucks.
Well, I always appreciate honesty, but seriously, I love Desmos. It's so much easier. Tables are just ugly.
Yeah, Desmo's been really easy with the math.
It does all the computations for you too, but I don't know if I mentioned, but you guys are going to be able to use Desmos on the exam, so when we start doing harder computations, we'll do them in Desmos. I think I was showing you how to do means and standard deviations in Desmos too, right? So
Yes.
in general, it's a pretty neat tool.
That last problem, can you like plug in the last one too?
Oh, wait, could you explain? I don't understand what you're asking me to do.
Oh, never mind. Sorry.
Yeah, I did. Yeah, it's displayed, right? I think we're good. Okay, Caitlin, I have not taken roll yet, so you don't have anything to worry about. I will take roll eventually, probably after the break. Okay, so that's that. Now, the only thing that's left is to do these reverse problems where I start by giving you a probability. So let me show you. And I'm not going to give you a Desmos command to do this. It's way too complicated. So we're just going to do these the old-fashioned way. I'm working my way back to my iPad here. It's a couple of steps. Okay. All right, so we're going and just finishing up by starting with the areas under the curve, but not knowing how tall the woman is. So what you need to do is just completely do the problem in reverse. Okay, so they're telling you she's 85th percentile. First of all, you need to know what that means, obviously. So 85th percentile, the definition of that, remember, percentile is just the percentage of people that are lower or scores that are lower. So if she's 85th percentile, she's taller than 85% of other women. So she would be above average in height. So I'll put her height here. I'm going to do a question mark for that. But notice how I put her above average. She's taller than 85% of women, so there's an 85% chance of someone being shorter than her. Okay, any questions? So I've already got the probability. What I need, again, to reverse the process, if you look at the, like the first one, the last thing we did was give a probability. Before that, we gave a z-score, okay? And then we had an x. So we have to reverse this. Right now we have the probability, okay? We have to get a z-score and then convert it to an x. So we're looking for a z-score that has an area to the left of 85%. So let me just see if I can find something like that. Again, she's above average, so her z-score is going to be positive. And we're looking for something close to 85%. Inside the body of the table. Now here's an 8508. That's pretty close to 85%. The next closest is the 8485. That's a little low by 15 ten-thousandths, where the 8508 is a little high by 8 ten-thousandths. So the 8508 is the winner. We're going to pick that one and figure out what z-scores go with, or what z-score goes with it. 1.04. So she's 1.04 standard deviations above the mean. Is there any question about that? And then from there, we can give it a height. Okay, so I'm gonna draw this in the notes real quick. So the step-by-step process is to put in, we're looking for a 0.85. I'll say it's approximately, I think it was a 0.8508. And with the 8508, we got 1 point, was it 1.04? Yeah. So 1.04. And again, these are z-scores, so you're not done yet. I can put this as a z number line and 1.04 there. So that's to the nearest hundredth anyway. That's the 85th percentile. Okay, any questions? But that doesn't tell me how tall she is. So I would just kind of remind you the formula up above to convert z to x. We use this formula. X would be her actual height. So x is mu plus z sigma. Let's go ahead and do that down here. And again, she's 1.04 standard deviations above the mean. So all you have to do is take the mean, which was 66, and add 1.04 times the standard deviation, which was 4 inches. Okay. And so let's see what that is. And just go ahead and shout it out if you get it.
Uh, 70.16.
Perfect. 70. She's basically she's 70 inches tall, right? We'll put inches, and this it's too precise, but go ahead and carry all the precision. It's just, you know, we're just kind of showing your teacher that you can get it to the nearest hundredth or whatever place you got there. Okay, any questions about that? You get to do one more. This one's a little slightly different because here it says that 35% of women are taller than the next lady. So we don't do areas to the right on these distributions. We need the area to the left. Now they're telling us 35% of women are taller than she is. So this is the picture that goes with the question. But I don't know what percent of women are shorter. So could anybody figure that out? Remember, the table only does areas to the left. This is an area to the right. It's not going to work. Did you fall asleep?
Can you explain one more time, please, the fact that the table only takes care of areas for the left? And
Well, just because that's how I made the table. It only has areas to the left. So the picture that always goes with this table is you're looking up any z-score, positive or negative. But regardless of the z-score you look up, the table is telling you the area to the left. So what I'm coloring right now is an area to the left of the z-score that you're looking at.
okay.
And that's just all the table gives. It can't give both, right? It has to do one thing. So it's just typical for us to give the areas that accumulate on the left side of the z-score. So we call that a cumulative distribution where you accumulate up to a point. Okay, is that all right?
Yeah, thank you.
Yeah, you just got to get used to it, you know. Anyway, so we have the area to the right. It's 0.35. I still need the area to the left because this table does not do areas to the right. It could, but it doesn't.
Would that be the 0.65?
Good. So we're doing 1 minus 0.35, which is 0.65. And now we're doing the same thing. We're going to the table and just searching for something close to 0.65. So second step, something approximately 0.65. Well, anybody see it? Tell me what the closest number to 0.65 is. Somewhere in here.
0.35. I mean,
So-
0.39. Sorry.
Yeah, so you're doing the 6517 here. I'm with you. So the 61517 is the closest to the 0.65, and that has a z-score of 0.39 there. So good. So I'm going to try and kind of minimize this here. 0.65 is closest to 0.6517, which relates to a z-score of 0.3 and up to 0.09. So Z is 0.39. She's only 0.39 standard deviations above average height. So now we need to figure out how tall she is. Okay, so you just, for that, it's the X plus X is always the mean height plus Z standard deviations because she is Z standard deviations above the mean. Okay, so the mean is 66 and then you want to add 0.39 standard deviations, and the standard deviation is 4.
Um, 67.56.
Yep. Okay, so she is the 65th percentile. That means 35% of women are taller than she is. Okay, any questions about that? And I'll do one of these on your exam. And that'll be the last problem probably. Okay, last chance for questions on this. You can do these in Desmos as well, but the process is just a bit ridiculous. So I think I'm just gonna vote to have you guys do these on the table. And if anybody really wants to see how to do it in Desmos, just let me know and I'll show you. I think, well, I'll just put it here in case anybody really wants to know. So in Desmos, you say, I think you do inverse CDF and then normal dist parentheses 0, 1, and then you have to give the area to the left. So you would put in the 0.65 here, which is the area to the left. Just gonna pause for a second to make sure that works. I have no faith in it, but inverse, and I'm not showing you CDF, yep. Dist 0, 1, 0.65, close parentheses, it says 0.39, which is what we got. Yeah, so that's how you do it in Desmos. And that's it's a big command to remember, and that's why I was reluctant to give it to you. Again, I'll give you the commands on the exam, and I don't even mind giving you this one, so you don't have to memorize any of the Desmos commands. Just make sure you've practiced using it. Okay, last chance for questions. Okay, so that's it for this chapter. I want to go ahead and pop back here. I'll show you the Desmos screen again, so you guys can see the horrible command I typed in Desmos here to get the 0.385, which I rounded to 0.39.